So I'm going to try my best to explain how reverse linked lists work and Heapify. I'm gonna try to talk about the parts that were confusing to me. So let's wait to see if it's streaming. So I found this GIF here from a lead code solution. And the way that it works pretty much is that you create 3 different variables, and then you use those 3 different variables to swap each node. So let me walk through the thing. So this is the beginning, and the algorithm is pretty much this loop here. So I don't remember if this one accepts the head, but the one that I have there, the code, it accepts the head, and then it creates 2 different pointers, one null pointer and one pointer that is just undefined. And then it loops over until the head's not null. So what it does is initialize this variable called next, and this is gonna be a pointer, and then it makes it equal to the current.next or current next, which is gonna be the pointer to the next node. So the current in this case would be the head of the linked list in the beginning, and then the swapping happens on these 2 different lines here. The current next becomes the previous one, and the previous one becomes the current, and then it uses the current again to update the next. So the last line here, the first line and the last line are just used to move the pointer, or the main pointer, into the iteration. And the other 2 in the middle are the ones that actually do the reversing parts. So like what was difficult to me to understand in the beginning is that when you're making this pointer equal to this one, you are copying the value of the pointer. So when you reassign the current next here to previous, this one is still gonna have the initial value of the current next here. So yeah, the illustration shows, I think, very well how it works. So in the beginning it was no, and then after this line it becomes this true. Then it changes the next pointer. So the current next is a pointer inside of the head node. So when you're doing this assignment, you're just changing the value of the pointer. And you can think about the pointer as being a number that represents an address in memory. So when you do this assignment, the only thing that is happening is that you're changing the value of that pointer to a different one, which is going to be the equivalent value of the address of the previous node, which was the variable you initialized at the beginning. Then after that, so this line is also kind of confusing, but this one, it moves the previous pointer to the current pointer, analyzing, because for the next iteration, when you want to reverse the next pointer, so it's the same thing, you're just reassigning the value of the previous. So instead of being null, it's gonna be equal to, it's gonna point to the one that is at the current iteration, which will be the head in this case. And the head is the current variable here. So it just goes from null to the current one. Then the current next is just moving forward the current node, which will be the head. In the other example that I'm going to show, it's just moving, advancing the iteration. And then that happens again until it reverses everything. So I'm going to explain with the code that I have there again, because it is quite confusing. It was very confusing for me to understand. The key thing you have to understand is that when you're reassigning a pointer to another pointer, you're not changing. If you change the value of the pointer you assigned the other pointer to, you're not going to change the original value. So this is the key thing to understand here, is that when you're assigning the next to the current next value, when you reassign current next, you're not changing next. Next is still the pointer to the original value that current next pointed to, which is the next node. And the same thing happens on here as well. They'll make previous equal to current, and then you change the value of the current. You're not changing the value of the previous when you do the current equals next, because on the assignment it determines where the pointer is going to point to. So it pretty much just does the same thing, and then at the end it dereferences the head So when you dereference, you get the value that the pointer is pointing to. So when you do that, then you change the actual value of the data. So the head pointer is the thing that is pointing to the location where you had the struct, which is the head of the node. And this is accessing the actual value of that struct and is reassigning to be equal to the previous, because the previous is going to be on the last iteration is going to be the current one, which was going to be the tail, but now is the head because you reversed the list. So hopefully that's clear with the GIF. So this is the example that I have here, just pretty much the same thing. I think I'm going to show on this one, but it's the same file. So on this one, it accepts the head node and creates the next nodes and the previous nodes, which are going to be pointers, and the previous node is pointing to null at first because the last node of the linked list is always going to point to null. Then while we still have the head, same thing here. The next node is going to be equal to the head next, and this head next is a pointer. So you can think about as replacing this as a value, and this value, for example, 100, or maybe this is like easier. This is going to be an address in memory. So when you do this here, this value is going to be undefined. It's going to be any value because they're not specifying when you're initializing. So you would be like 400, for example. So when you do this, you're just making the next node to be equal to this value here, which is a number that represents this address here. And this address contains the next struct of the list on its actual value in the place of memory. But the pointer itself is just the address. So after you do this, then when you reassign it here, it's the same thing that is happening. So this would be 100 in the example that I gave there. So you're reassigning to the null pointer. So this is also not null. It's going to be an address that contains a null in the value. And you're reassigning the 100 address from the next node should be equal to this one. Then same thing here. You change the value of the previous to the head, which is the current node you're analyzing, because that's going to be the next one in the iteration that you want to reverse the pointer. And then after this line here, it just moves the head pointer to the next node. So it makes it so that it points to the next one in the list, which was the one that it was assigned here. So in this case, it would be the 100 address. Just making the head, because this is the pointer, again, it's not the value in the memory, it's just a pointer to the value in memory. So it's replacing the pointer to the head node with the 100 address in the example that I gave, which will be equivalent to the next node in the list. So this assignment doesn't change the value of next node by proxy because next node is a different pointer than head next. That points to the same address that head next points to. When next becomes equal to prev node, next node doesn't change because it's a separate pointer. That way, head next becomes the prev node pointer, but next node is still the old head next pointer. So hopefully that's clear. And this here is very similar to swapping an integer. So it's the same pattern. Like the first line and the last line are just temporary variables that you have to use to move the pointers forward. So you reverse all of them. So that's, and you have to do that because you're going to reassign the values of the other pointers. So if you didn't have these variables here, you would lose the information when you change the pointer. So you need to create a temporary, then you swap the values here. The next becomes the previous, and the previous becomes the current one. And the other ones are used to just move the main pointer forward. That is going to determine which node is the time to reverse the pointers. So hopefully that's clear. It's very confusing, so like if you want, you can spend a bunch of time, then you're gonna understand. But hopefully, did a good job of explaining the main parts of confusion that I have. So now let me explain the Heapify, which was another one that was kind of confusing to me. So a heap is just I'm not 100% sure if that's the only way to represent, but the way that I've seen there on the example is a way to represent a tree in an array. So think about the concept of a tree, but if instead of representing as a tree, you represent it just as an array, as a linear structure. So what's happening here actually is just to have the concept of a tree in your mind. And then the way that the indexes work is that the root node is going to be the 0 index, and the other ones are going to be like a zigzag from left to right. So it starts at 0, then 1, 2, 3, 4, 5, 6, and so on. And because of the way that you organize the indexes like that, you can convert the values from this concept of the tree into a linear format, which will be the array. So you can see here that this would be like this one, and then like you're just taking the nodes and putting them side by side like this. That's pretty much the transformation you're doing. To instead of having the tree, you represent them in an array. And because you do this translation, like how are you gonna know which index is the parent and which ones are the children? The formula to making the translation from the tree concept to the linear format is gonna be the index times 2 plus 1 for the left node, and index times 2 plus times 2, yeah, times 2 plus 2 for the right node. So here you can see that it's kind of intuitive. The reason why you multiply by 2 is because each node has 2 children, because it's a binary tree. A binary tree is whenever you have a tree that every parent has 2 children. So because of that, since the tree is going to grow by the factor of 2, it makes sense that in order to find the index of the child from the parent, you have to multiply by 2. So for example, in here, you would multiply 0 by 2, you would have 0. And theoretically, that wouldn't be the children in practice. And the reason why you have to, and this is the point that a confusion that I have, the reason why I have to do this plus 1 here is because of the 0 index. So because the array starts at the 0 index, you have to increase by 1, the left, to offset the 0 index. So if arrays started with index 1, then it would just be the multiplication by 2, because the tree grows by the factor of 2. But because the arrays start at the 0 index, you have to do the plus 1 to offset that index. And then you get the left node, and then obviously the right node is just going to be a plus 2, because then is the one on the right of the left, obviously. So that's the main thing that's is kind of tricky to understand about binary heaps. So based on this calculation, you can convert from any index you have on an array, you can know what their children is going to be just by applying this formula here. And then obviously if you have the child and you want to get the parents, you just reverse the equation. But it's the same formula. So if you have an index that is outside of the array, then the node is just going to be no. So that's the hardest part to understand. And heapifying, the process of heapifying is because binary heap can be either a max heap or a min heap. And a min heap just means that the minimum value of the heap is at the root. And the max heap just means that the maximum value of the heap is at the root. So in order to ensure that this is the case, you have to do this process of heapifying, which just means that you're going to shift the nodes around until you have the minimum at the root or the maximum, depending on what kind of tree it is. And the way you do that is just by this function here. So based on the current index of the current node, you're going to get its children by applying a formula that I just explained. And you assume that the largest, because this is a max heap, this example, you assume the largest is the current index, and then you compare the values here. So this is just to see if the index exists, I think. Yeah, because n is the length of the array. So first you check to see if the indexes exist, or if the node exists, the child exists. Then you check to see if the value is greater than the current one. That means that you have to change, because obviously you want the highest node at the top. So if the value of the children is greater than the parents, then obviously you have to swap them. So you reassign the value of largest. And then if the condition is true, then that means that the children is a higher number than the parents. So you call the swap function, which just swaps the values of them on the array. And then you call Heapify again because you're just traversing from that point all the other nodes on the subtree. And then heap sort is just going to be applying this pattern here of rearranging the tree configuration in order to keep the property of the maximum node being at the top. And then you're going to loop over again, and you're going to repeat this process each time. So you're swapping the node at the root, which is the highest value. So this is for sorting an array. So you're swapping the node at the root, which is the highest one, with the last node, because this starts at the last. And then you call the process. So first you structure the tree so that the zero index is the highest node. Then you swap the first index with the last one, because then like you want to reverse the array. And then you call Heapify again so that you have the same structure, but now you're excluding the node that you just swapped, which was the highest node, but now is the last on the index. And you're rearranging so that the next iteration, the zero index is still going to be the max. And you do this over and over again. So like the I pointer is going from right to left. And each time that it does that, the remaining sub-array is going to be a heap. So because it is a heap, a max heap, the zero index is going to be the highest, and then you swap the zero index with the most left one, and then you do this over and over again, and then by the end you're going to have the array, because all the max values were swapped to the right. So I think that's pretty much it. So hopefully it's clear. So yeah, I'm going to stop here. Maybe I'll come back today to do some other stuff, but we'll see. So see you next time.